All right, hey everyone. I've gotten a few questions on constitutional isomers and people having difficulty being able to identify them and draw them. It is something that is fairly difficult to do. It's something that I think practice makes perfect on. I think your challenge assignment I designed specifically because I think it's great for practicing constitutional isomers, which is just this idea of let's start with molecular formula. How many different ways can I draw this compound? We can make it a little bit more difficult. How many ways can I draw this compound? That is the best way to practice connectivity of atoms, as well as being able to identify constitutional isomers versus just identical drawings. I do want to go over a little bit of tips here, though, as one way to do it. So first of all, let's start with some target molecule. If I was just given something C3H, this should be 7Cl. My first step would be to just come up with something that works, okay? So boom. Oftentimes, the easiest way is to do your carbons in a straight chain to start out with. Don't try to do anything crazy with closed rings or anything like that. Just start off with the straight chain. The other thing that I want to point out is that the structure of these organic molecules are such that you have some atoms like carbon that like to have more than one bond, so in this case 4 bonds. Well, those are going to have to sit like on the core of the molecule, inside. And then they're going to be decorated with these hydrogens, which can only have 1 bond, as well as the halogens can only have 1 bond. Oxygen and nitrogen, they're a little bit in the middle. They can reside in the middle of the molecule, and they can sort of sit on the outside as well, as long as they have like an OH, for example. But nonetheless, that's one of the sort of distinct ways to think about it. Never, ever am I going to have a carbon here, right? Just sitting on the outside. So that's got to be sort of insulated or tucked in by some other atoms. Okay, so first of all, one of the things to, we either can draw a constitutional isomer or an identical molecule. Remember, constitutional isomers have different connectivity. So that means an identical molecule will have the same connectivity. So what does that mean? Well, if I just were to swap these two here, all right, so let's just go ahead. I'll actually do this. Draw a bunch of different ones. All right, and let's swap the chlorine and the hydrogen. There's no different connectivity here. I still have a chlorine bound to that terminal carbon and 2 hydrogens bound to the terminal carbon. All I've done is drawn it differently. Even more, a little bit weird, is if I were to, probably gonna have to do some more rearranging, but what if I swapped even like this carbon and this hydrogen here? That would change the way that it looked in terms of its drawing quite a bit. How am I going to do this? But it doesn't change the connectivity of atoms, right? I still have that terminal chlorine on that terminal carbon, and still have 1, 2, 3 carbons in a row here. It's just drawn differently, and honestly a little bit weird. You can see why we wouldn't draw it like that, because it sort of gets things really crowded. So these would be 2. So if this is my target, these are 2 examples of identical molecules. It's just the exact same thing as I had before in my target, just drawn a different way. So anytime you're swapping 2 atoms about the same, that were connected to the same atom, and you're just swapping their bonds, that doesn't change connectivity. All right. Now, if I were to take this chlorine and swap it with a hydrogen on a different atom, that would usually produce a constitutional isomer. And I'll tell you why I say usually instead of definitely here in a second. So this would be an example of a constitutional isomer. Now my chlorine is bound to that central carbon, not one of the terminal carbons, okay? This is also where model kits are really great, because if you had a model kit and you built this atom right here, and you had a model kit and you built this, molecule right here, or this molecule right here, you would realize that you built the exact same thing. Whereas if you built this fourth one here, it could never be, you know, superimposed or the exact same as that other target molecule. So this is a constitutional isomer. And this word isomer, I just want to say real quick, because you guys, I'm sure, have heard it in the past. First of all, you definitely heard it in Gen Chem with respect to atomic isomers, right? So atoms that have the same number of protons but different neutrons. We're not talking about that. This is a molecular isomer. There are also many different types of molecular isomers. So maybe, I think some of you have mentioned this idea of like cis-trans. That's a stereoisomer. We'll get into that. Don't worry if you don't know what that is. This is just one type of isomer, meaning that they share molecules that share this same molecular formula. We'll be introduced to more and more of them as we go, and they're going to be even a little bit more complex. But this one, again, when we talk about our constitutional isomer, we're talking about different connectivity. So then you could go through and sort of, okay, well now what if, so that's sort of what I would do in terms of how I'm going to draw all the different constitutional isomers. I'm going to start with one that I know is right, and then I'm just going to start swapping positions of things. Now before, when I said that if you swap two atoms on different molecules, you will probably get a constitutional isomer, but not always. So this would be an example of one where I don't. Let me show you why. So now I'm going to swap these two. So this is actually identical to my target. And that's because it's just the mirror image, right? The exact mirror image, I guess, in terms of how it was drawn up here, would be if these two were swapped, right? Now, hopefully you can see, when I get done here, hopefully you can see that these are indeed, this is indeed a mirror image to that target molecule. But then again, just as we had said before, this picture here is just these two positions swapped. So that connectivity is the same. So that is another thing that's going to be challenging about this, is being able to spot when a molecule is identical to the target and things are just kind of drawn in a different position. I promise you'll get very good at it. It's not something, it's something that's a little bit weird at first. The whole semester, all we're going to be doing is looking at these structures. So being able to decode the information in these structures is something that's going to come with practice, and practice makes perfect. At the second semester, you're going to be amazed with how easy it is for you to do this sort of thing. But these are the skills that we got to build now. So again, practice, practice, practice. Get a bunch of these different molecular formulas and just try to draw all the different things, you know, connected in all the different ways, and identify what you've drawn as being either identical or a constitutional isomer. So these are, so just to finish off this problem here, there are actually only two constitutional isomers. This one is also identical. So my pair of constitutional isomers would be this one and this one. And just to note, I could have picked any one of these and paired it with this one, because again, they're identical, meaning they're the exact same way, different ways of drawing the exact same molecule. So those were all pairs of constitutional isomers. Yeah, I mean, so I guess I'll do another example just to make it a little bit more tricky here. So there aren't just the two, and we can see. All right, so let's do C3H6F2. So again, step one is just going to be to draw anything that works. All right, my strategy, easiest one, all your carbons in a row. First place to start. Oh, actually, let's do this. Oh, crap, that's one of your challenge problems. I can't do that one. Well, sure, I guess we'll just do that. Okay. All right, so again, first place, just start by laying down all your carbons in a row. That's usually a good starting point. And then decorating with hydrogens. Note that if for some reason I wasn't able to do this, let's say that I didn't have enough hydrogens, that just means that there has to be double bonds in there. All right, so remember your rules for drawing Lewis structures. Okay, so now in this one, I don't really have the same sort of single bonded one that I can just move around, that halogen. But nonetheless, I'm going to play the same game of swapping things that are, again, bound to different things. So instead, and now I'm going to, because I can't really rearrange the atoms that are decorating the outside, that's the easiest thing to do. That's the first step in finding all your different constitutional isomers. Now you got to rearrange that framework in the middle. Okay, so there is another way that I could have connected my carbons that would have been legal, and that would have been, what if I swapped this hydrogen and this carbon, right? Or another way of thinking about it is just that I'm going to connect my carbons instead of going in a straight line. Now I can put one down there also. And then you're going to fill in with the hydrogens. Okay. So anyways, this is just an extra little aside. I will say that your book both, actually, let me get you the exact pages. On page, I believe it's 41, down at the bottom, it sort of lays out a good strategy for drawing all these constitutional isomers. And then, there's another, please. Yeah, section 1.1 might be a good thing to read as well for sort of developing a strategy for these constitutional isomers. And that starts on page 3. Okay, so yeah, so again, one of the nice things about this course is that we will be, in terms of material, going in the same order as the book. So my intention is for you to look at the lectures. Hopefully that's enough for you to be able to do those quizzes and discussions and assignments and all that good stuff. If it isn't, your next step is to turn to the book, because there's going to be the exact same section, just like, you know, there's a hybridized atomic orbitals movie, there's going to be a hybridized atomic orbitals section in your book. And so that should be extra additional information. And then obviously Google, YouTube, all that other good stuff. But yeah, so hopefully this helps a little bit.